So we are doing 6.2. In your books, this is 1.3. Your homework will again be out of your book. How the whole unit is. Notes are kind of long today, but not really that hard. So a lot of it you've seen before. Scenic and behavior. I know that one. Right. And behavior. Good. Do you want something? All right, guys, you ready? 3 L's and an A. 6.2, continuity and behavior and limits. We're sort of touching into limits today. We aren't formally. All right, guys, so the first thing we're going to do is continuity. Jot down just the title, continuity. I think this is kind of hard to read for you. So I'm going to read through it, and then I'm going to write sort of a shorter version that I'd like you to write. So what we will be checking for is to see if a function is continuous at a specific value. So this is talking about at x equals c. It's continuous if your function is defined at that point, if the limit exists at that point, and then if both of those things are the same, then it is continuous. So again, let me write it in like a shorter way. So your continuity test. You have to check these 3 things every time. So the first, you have to find f of c and show that it exists. So f of c must exist. When the limit of your function as x approaches c, that exists as well. The third point is that f of c equals the limit of f of x as x approaches c. So 1 has to exist, 2 has to exist, and then 1 and 2 have to be equal. So all of this, if that's true, then the function is continuous at c. Or at x equals c.
What's the difference between the second one?
So the second one is just saying the limit exists. The third one is saying the limit, like what the limit was and what the function value were are the same thing. So like you've got 0.1, 0.2, 0.3 is that 1 and 2 are actually equal. Okay. And when we do an example, it'll make more sense. Okay. All right, so let's do an example. So your function is I want to know, is it continuous at x equals 1? We're starting with a nice simple function. All right, so 3 bullet points. Every time you do this when you're showing work, show me those 3 things. Don't make me hunt for them in your work. You have to show me in an organized way. 1, 2, 3. Okay? So first bullet point is we're trying to show that f of c exists. So guys, realize this is your c. Like, okay? So what I'm looking for is f of 1. How do I find f of 1? Plug it in. So 2 times 1 plus 3. So what does f of 1 equal? 5, okay. So does it exist? Yes, it exists, okay.
If it didn't exist, what would it look like? What you said?
So not existing, more often than not, you're going to see either in a piecewise function or something that if you graphed it would have an asymptote, like a rational expression, that sort of thing. This, we're starting with a basic one that's going to work, okay? And guys, if you're going through this very first bullet point, if you recognize that f of c does not exist, you don't have to do the rest of the problem. You can just say it doesn't exist, not continuous, okay? All right, so the second one, we have to find the limit of our function as x approaches 1. Okay, you guys don't really know what limits are yet, so I'm going to give you the basic rundown of what a limit is. If we were to graph this, what does y equals 2x plus 3 look like? A line. Where does it start? Y-intercept of 3. Slope of 2. Let's just do that. 1, 2, 3. We start there. Up 2 over 1. That's our line, right? Okay. So when I'm talking about a limit, you're squeezing in to see what the graph is doing as we get really close to a point. Not exactly at that point, but what is happening as you approach it from the left and from the right. It's like you're just squeezing in. So what I'm looking for here is as x approaches 1. So I'm going to even zoom in on my picture for you here. Okay, got a little blurry. So as x approaches 1, when we squeeze in, what y value are we getting closer and closer to? 5. That's it. That's the limit. Okay? That's all you have to do. What y value is it getting close to? And guys, I'll show you some where the limit doesn't exist. But that's it. It's right there at 5. So the limit, of
You have
f
to
of x.
show the graph, or you can just say.
No, and sometimes they'll even just give you the graph to evaluate it, like your function, instead of giving it to you algebraically, I'll be like, here's f of x, and I'll have a graph of it piecewise for you, so you can just look at it and tell me. But there's not really any work to show me the limit.
So, if you're like given the algebraic way, you just plug in the x value and whatever you get is not your limit.
Well, it depends on what your graph looks like. Simple ones like this, it's going to be the same.
So, you know how you put in like plug in 1
Yes.
times, so would that not be the case for
For others, it's not always going to be that simple. Okay. All right, guys. So bullet 1, bullet 2, were they the same?
Yeah.
Okay. So we would say f of 1 equals the limit of f of x as x approaches 1. And you can say therefore, which is the 3 dots. Have you guys seen that before? Therefore, f of x is continuous at x equals 1. But guys, all of that needs to be included in your answer. Okay? The 3 bullet points in your conclusion. Stay organized. Don't make me search for these things. Okay, you ready for another one? All right, so this time I will give you a graph. I'll tell you this is g of x. question there, is g of x continuous at x equals 1? Just looking at the graph, what do you think? Is that a continuous function? No. Okay, so no, the answer is going to be no, but now you have to show it with the continuity test. So let's go through our bullet points here. So the first one, and instead of f of x this time, we're using g of x. So I need to find g of 1. What does g of 1 equal? It equals something. Negative 1. Do you see that other dot? Yes. Okay. So g of 1 equals negative 1. Everybody's okay with that, right? Okay, then the limit piece. So the limit of g of x as x approaches 1. So remember, limit is as x approaches 1, not as it equals 1. So as we approach from either side, what is your graph getting closer and closer to? 1. I know it doesn't equal 1 at that point. That's okay. The limit is what is it getting really close to on either side? It's approaching 1. So that's the limit.
You're limiting something, you're only looking at the graph.
Yeah. Later you'll learn about doing them algebraically, but for right now, just graphically is all you're going to do. So the limit of that is 1. Does that make sense, guys? You can have a hole and you still have a limit at that point. It's just what is the overall graph approaching. Okay. So what's the issue here? Why is it not continuous? Right. So you would tell me g of 1 does not equal the limit of g of x as x approaches 1. Therefore, g of x is not continuous at x equals 1. When I'm doing the limit, okay. So think about if I'm tracing this. Like if I'm tracing from the left and I'm tracing from the right, does that have anything to do with this one? So think about following your graph. What is it getting close to? I don't care what actually happens at that point, just what is it squeezing in. Okay, I know it's weird. It gets easier. Your brain wraps around it a little bit. All right, we okay? Do you guys want just a couple of picking up a limit from the graph practice? Okay, so let's just draw through. Let's do. So find for me x approaches 2. Actually gonna do squeeze 3 of them in here. All right, guys, try to answer all three of those real quick for me. So let's go through them. What do you think for the first one? What's the limit as x approaches 2? 3. Is that one easy? Okay. What about the second one? 1. Now, were you a little stumped on the third one? So, and I haven't shown you one like this, so that's okay if it's tricky. So if we're coming from up here, it is 3, right? If we're coming from down here, it's -2. Do those meet at the same point? No. So it does not exist. The limit does not exist. Piecewise, it depends on what I asked you. Like if I had said find the limit as x approaches 0, it'd be 3. Okay, because like as you come close to 0, both sides, it's 3. But at as x approaches 2, they do not match up. So yeah, like where the endpoints are essentially, unless they happen to meet at the same point, it's not going to.
Why wouldn't it be 3? Because isn't the dot mean that there's a point there?
So for the limit, you have to trace it from the left and from the right. You have to squeeze in from both sides. Okay? So as we come from the left, it's absolutely 3. But as we come from the right, it is -2. Since those do not meet, it doesn't work. Like on this one, if I come from the left, from the right, do you see how they run right into each other? Okay? Whereas here, they do. Okay? Again, limits are new. Like I know this stuff a lot to wrap your brain around. So. You okay with those? Okay. Do you need one more continuity practice? Or are we okay with it? Do you want one more or not? Okay, I heard one yes. We'll do one real quick. We'll make it a piecewise function. So what, is this our third one? So is f of x continuous at x equals 1? And I think you guys know the answer right away. It's going to be no, but you have to show me why. So as you squeeze in from the left and from the right, did they run into each other? No, they're at different places, so that means the limit does not exist. It has to be the same value that you're getting close to from the left and the right for the limit to exist. Okay? They're all pretty, I mean, if I give you the graph, you know right away if it's continuous or not. So the algebraic ones may be a little trickier, but continuity test should be pretty straightforward. It's just a matter of like making sure you show those 3 steps. Okay. So guys, if we go through this one, first one, we have to find f of 1. What is f of 1? 3. Okay. So we're okay on that one. And then our limit. So the limit of f of x as x approaches 1 does not exist. Everybody see that? It's different from the left and the right. Okay, so does not exist. So we can stop there and say therefore f of x is not continuous at x equals 1. It's continuous in other places, but it is not continuous at that point.
All these continuity tests, they're all doing functions, right?
Mm-hmm.
Yep.
Okay with that?
Would that be a question or it would be a function?
I'm not going to give you any that are not functions. Okay. All right. Okay, so now we've looked at these functions that aren't continuous, and we have specific names for those types of discontinuity. Do you guys remember those from last year? Do you remember, like, jump and whole or removable? Remember any of these? Okay. All right, let's see. I think I just want to rewrite it for you. So. All right, so we have discontinuity. The first type is called infinite. This is an asymptote. So it happens when the denominator equals 0. And graphically, what it would look like, let's say your function was 2 over x plus 3. So if you were answering like the type of discontinuity, you always have to give me the location. So for this one, you would say infinite discontinuity at x equals -3. And again, I'm going fairly quickly through the discontinuity because this is somewhat familiar to you guys, right? Yes. Okay. No? Okay. Does the first one make sense? Okay, all right. They're not really bad. It's just identifying the type and then where it happens. That's all you have to do with your discontinuities. So there's no, bullet point, step-by-step process for this. You just tell me what it is and where it happens. The second type is a jump. And these are going to happen in piecewise functions. So let's say you're given the function x plus 4, x is greater than 2, 2x minus 3, x is less than or equal to 2. You've got two options for figuring out if there actually is discontinuity here. One is you could actually graph your piecewise function, okay, and look at it and see, okay, did the two pieces happen to overlap at that point, or is there a jump in between them? The other way is you can look at it just algebraically, and you can plug in your 2. You guys understand that this discontinuity would be happening at x equals 2? Okay. So if I plug the 2 into the top equation, you guys see I get 6. And if I plug the 2 in down here, I get 1. These do not match, do they? Okay. So without graphing it, you know that it is discontinuous. Like there's a jump at x equals. You are certainly welcome to graph it to look at the discontinuity as well. Okay. It's easy to remember. It's called a jump because there's literally like a big jump in between the 2 points. Okay, so far. The third kind is called removable. You can think of it as a whole. We've definitely talked about those in graphing before. This happens when you can reduce factor from denominator. It's like when you're able to cancel out one of those factors from both the numerator and denominator. So let's say your function is something like x plus 2 times x minus 6 over x minus 6. I could cancel out these factors, right? So then I would have removable discontinuity at x equals, what do you think? 6. Okay. And stop me if I go too quickly through any of this. I just think you know this, so okay. Stop me if you have questions, please. And guys, graphically, that would literally look like a hole in your graph, because what you have left would be the line. And you would just have a hole in it, okay? All right, okay. Questions on the types of discontinuity? Would it be what? I'm sorry. So kind of two separate things. Like I would give you, is this continuous? Like is this function continuous at a specific point? And you'd have to go through the bullet points. And then just like a separate question, I might say, name the type and location of discontinuity. And so you wouldn't have to do the like 3-step thing. You could just tell me, okay, it's infinite at x equals 2. Sorry, we've done enough of those, so let's do a couple of these. So let me make up one for you. What are we on? 4? Rectangles. All right, so name the type and location. And guys, I might give you a question where it's a continuous function and you would just tell me there isn't any, like none, okay? All right, so let's do x equals. Again, guys, do you need to graph this to figure out if it's continuous or not?
No.
No. What do you think, guys? one vote for jump at 2, and then I have a head shake.
Yeah, it's just both slide.
They both end up being 5. Yes, I was trying to trick you. Don't let me. You don't have to. You can just say continuous. Like that would be your answer. And algebraically, you're right. If you plug a 2 in here, 2 times 2 plus 1, you get 5. This one obviously just is 5. If you thought about it graphically, what's happening here? It's going that way, and then it gets filled in, and it's going that way. So it's got a lovely little corner there, but do you see how it's continuous? When one fills in the other one. Okay. So yes, don't let me trick you. The homework's just what's on the assignment sheet, okay? All right, good luck. Run fast. All right, guys, what do you think on this one? Is there more than one answer?
Yeah.
Yeah. Okay. Should we go through it together? You seem hesitant. If I factor the numerator, what does it factor into? X minus 1, x minus 1. The x plus 2, x minus 1 won't we do the right thing at the end, so. Denominator, what does that factor into?
X minus 1
All right, so these cancel, right? So from that we have removable at x equals 1.
You said 4, 5.
What? Okay. And then I still have something left in my denominator, so I have infinite x equals negative 1. So you'd have an asymptote there, and you'd have a hole if you were graphing this. Okay. Okay. We still have a denominator, right? What would make your denominator 0?
Oh,
Yep, that's the infinite, remember, is just like the asymptotes. So that's where that comes from. All right, guys, questions on that? Do you feel okay with discontinuity? Okay. We're going to do end behavior next. Alright guys, so you can have an even degree. When I'm talking about even, when it's a polynomial, we're looking at the highest exponent that you have, okay? That's what determines the even or odd. Even, it could look, if it's positive leading coefficient, the graph you should think of, it's just a happy old parabola. And if it's a negative leading coefficient, then it's just an upside down parabola. only thing that might be different is how we actually use our notation this year. Did you guys use limit notation at all in Algebra 2 last year? No? Yes? No? Not at all? Okay. So the way you would write this, if I asked you for the end behavior, I'm asking you for the limit of our function as x approaches infinity and the limit of our function as x approaches negative infinity. So that means as you're going really far to the right and then really far to the left. That's what end behavior is. So what do you think? As we go really far to the right, where's your graph going? Infinity. And as we go really far to the left, so where's it going? Also infinity, right? Okay. So then same thing, if you have a negative leading coefficient, same notation, limit of f of x as x approaches infinity, and limit of f of x as x approaches negative infinity. Where are both of these going? Yes. Okay. Easy enough? So that's if you have an even degree of your function. We know there might be a lot going on in the middle of your graph, but we don't really care about that when we're doing end behavior. We just want to know at the very end what's happening. Okay. The other option, you can have an odd function, like odd degree function. We have a positive leading coefficient. Graph you should be thinking of. You can even think of just a line or x cubed. And then a negative leading coefficient. We just have to flip. And then same idea, limit notation here. So the limit of our function as x approaches infinity, as x approaches negative infinity. Degree? Yeah, so biggest exponent. If you have polynomials, a whole bunch of terms, just look at the biggest one. So what do you think? As x approaches infinity for the first one, where's your graph going? Infinity. And as x approaches negative infinity? Yep. Okay, then same thing for negative leading coefficient. Limit of f of x as x approaches infinity. What's that one going to be? What? Okay, negative infinity, good. And then as x approaches negative infinity, positive infinity. Okay, again, we're going through this quickly, but are we okay? We're going to practice a couple of these. You don't need to write them down, though. Just we'll verbally practice a few. Okay. All right. So what if I gave you... So guys, if that's your polynomial function, well, I'm not writing straight. So as x approaches infinity, where's your graph going? Positive infinity. As x approaches negative infinity, where's it going? Okay, good. Don't get tricked if they're out of order. This is the one we're looking at, right? So positive goes the highest. Yes. Fine, the biggest. Let's do one more. Okay? So as x approaches infinity, where's it going? Okay, and as x approaches negative infinity? Easy? We're good? Okay. Alright. Okay. The IVT. There's a little more. This is the last thing we're doing today. So it's the intermediate value theorem. You will use this a whole bunch in calculus, so you have to start understanding it now. I know it's small. If you can't read it, let me know, but I want you to copy down what the intermediate value theorem says, and then we'll do an example with it so you can see how you're going to have to use it. It says if f of x is a continuous function and a is less than b, and there is a value n such that n is between f of a and f of b, then there is a number c such that a is less than c is less than b, and f of c equals n. I know it sounds terribly confusing when you first look at it. Jot it down. I'll explain after you write. And guys, go ahead and jot down the corollary too. Yeah, I would draw the picture too, and then again I'll explain what it means. You ready for an explanation yet? Not quite. You know, it's a long distance. Alright guys, let me start explaining so we can hopefully get through the last example here. So f of x has to be a continuous function. So as you look at that graph, that nice blue curve, that's a continuous function, right? No discontinuity there. Then it says a is less than b. Well guys, here's a and here's b. Would you agree a is less than b? Okay. And then there's a value n such that n is between f of a and f of b. Well, if you look, there's f of a. Isn't that just the y value when you plug in the x value of a? Okay. And then there's f of b. That's the y value that we're talking about again. So here's n. It's another y value. And does that make sense? It would be in between those two other y values? No. Not necessarily in the middle. Just somewhere in between. Like if one is -2 and one's 5, it could be 3. It could be 0. It could be 1. It's something in between those values. Okay? And then what you're finding at the end there, it says then there's a number c such that c is in between your a and b. Well, if your y value is in between, doesn't it make sense that your x values can also be in between? That's what it's talking about. It's saying we found this x value in between these other two x values. Okay? Let's do an example with it so that you can see what we're talking about. And the corollary, what that's talking about is specifically finding a 0, not just any y value in between. Okay? All right, so let's do one. Okay, so f of x equals x squared plus 2x minus 3. Does f of x equal 0 on the interval -1 to 3? All right, this is like the continuity test, very much a step-by-step process that I want you to follow and be organized with. Like, don't miss points anywhere along the way just because you didn't follow the steps. So, first thing you're always going to do is look at these two endpoints. We've got a -1 and a 3. I'm going to find f of -1, and I'm going to find f of 3. So if I plug a -1 in there, what do I get? -4. And then if I plug a 3 in there, what do I get? 12. So close. So guys, what that is telling me is that my y values are going from a -4 to a +12. So is it going to equal 0 somewhere in between there? Yes. Okay, so we know that yes, it's going to exist. We now just have to show the process that it does exist. So your very first bullet point, remember the first condition for this was that it had to be a continuous function? Looking at that, the x squared plus 2x minus 3. Do you think that's a continuous function? Yes. You have to state that. You have to say f of x is a continuous function. then the next piece, remember in the IDT it talked about one y value being less than another y value, so that's what we're going to show. F of -1 was less than 0, which was less than f of 3. It may not always be that the first one gives you a y value less than the second one, so that's why you always want to check. You know, if this had been the -1 and this had been the +1, you'd have to switch where, you know, the f of 3 and f of -1 were. So that's why you always check that first. Then what that means is, third dot, so there exists a C, -1 is less than C is less than 3. That just means there's an X value in between -1 and 3 that we're looking for. Fourth bullet point, such that f of C equals 0. Fifth thing you have to say is by the IDT. So, like, word for word, that is what you should be doing every time. Your values will change, but the format of that will be the same every time you do an IDT test. Intermediate value theorem.
If it is not continuous,
If the function is not continuous, you cannot use the IDT.
then you just say it's not continuous.
You would have to state that, and then you would use it. So, okay, guys, I know that was long today. Hopefully a lot of it was familiar and you've been refreshed on it. Your homework is on your assignment sheet.
Is it textbook problem?
It is, the full unit is textbook problems.
Wait, what if we don't have the textbook?
So you have an online textbook. Yes. You do. I gave you login information. I put